Greetings. Welcome back to Intro to Speech Understanding. So, in the past several classes, we have started to see how one might go about automatic speech recognition. Two lectures ago, you might remember that I showed you how to analyze a musical signal. If you're given a major chord or a minor chord and you want to know what notes exist as part of that chord, you can do it by taking the Fourier transform of the chord. The Fourier transform means that you multiply that signal, the waveform, with a set of cosines and sines at different frequencies. And at whichever frequency you get the maximum product, right? If a cosine, if the signal has a cosine at a particular frequency or a sine wave at a particular frequency or both, then you know that that signal contains that note. In the last lecture, we talked about how speech is also made up of the sum of sine waves at different frequencies, especially vowels. For fricatives and stop consonants, speech is a little bit different, but for vowels, it really is the sum of sine waves at multiples of your pitch frequency. So right now, I'm probably speaking at maybe a C note, one octave below middle C, or probably somewhere between that note and well, yeah, right around there, I guess, right around 125 hertz. So right around one octave below middle C. And that means that my vowels, as you hear them, contain cosines at 125 hertz and at 250 hertz and at 375 hertz and at 425 hertz and at every multiple of 125. This week, we're going to start to talk a little, we're actually going to create an automatic speech recognizer. I'm going to tell you how to detect speech in a signal using what's called a voice activity detector. The voice activity detector really just looks for high energy sequences in the audio. And then we'll create an automatic speech recognition model. We'll just take spectrograms of vowels and we will average them in order to create an average Fourier transform of a vowel. And we'll use that average Fourier transform as a template. And then we'll look through a test utterance and try to find out which vowels are contained in that test utterance by matching every frame by frame, we'll match that frame against the vowel templates that we have available. So let's get started. Let's start out with voice activity detection. So first of all, I'm going to import, again, the Librosa package. This is the package that we use when we want the most flexibility possible in doing audio signal processing. And I'll use that to read in a waveform file called train.m4a. Remember, Librosa is the only standard Python package that I know of that can read in M4A and MP4 files. So let's see if this works. Let's see if it'll import Librosa and then import the IPython display and then allow us to play it.
A, E, U, A, O.
So again, this is the same waveform that we used last class. This is my voice reading the five vowels, A, E, U, A, O, with silences in between them. And those silences are going to allow us to easily segment this speech into five separate syllables, and then to create a template that allows us to match, to identify in any future utterance which of those five vowels is being produced. So let's go ahead and plot the waveform. If we plot it, it looks like this. Here's the ah, e, u, a, o. And you notice that speech is much louder than the background noise. The background noise is almost silent, not quite. You can see little bumps and different kinds of noises in the background. Here's another little bump, but there's not very much. Those background noises are usually much, much quieter than the speech. And so all we have to do is look for the loud amplitude of the speech. Now, notice that it's not always positive, it might be negative. So we can't just look for high values, we have to look for high squared values. And so we'll take x of n, the speech signal, and we will square it in order to make it positive. And then we'll take the average over one frame from, say, n equals m to n equals m plus capital N minus 1. So over a frame that starts at time little m, right, starts at time little m, and goes capital N samples starting at time little m. So little m is the beginning of the frame and capital N is the frame length. We're just going to calculate the average energy by basically taking each frame. We're going to chop the speech into frames using this same code that we used last time, speech frames is equal to a matrix, which is the NumPy array created by taking a list of NumPy arrays. Each of the frames starts at time m and goes for a duration of frame length, where frame length is 25 milliseconds, and the frame skip parameter is 10 milliseconds. So m will be in the range from 0 to the length of the speech with a skip parameter of frame skip. In between the start of each successive frame, we'll skip 10 milliseconds, and each frame will be 25 milliseconds long. Then we'll compute the energy by squaring the samples and then taking the sum. We can take either the sum or the average, take the sum or the average over that frame, and that'll give us the energy. Those energy is computed once per frame, remember, so we have to take frame skip steps, frame skip samples in between the start of each successive frame. So if we started out with 8,000 samples per second, now we're only going to have 100 frames per second. And we'll plot the speech time axis and the speech, and then on the same axes, we'll plot the energy time axis and the energy. So that'll give us the speech time axis will be 8,000 samples per second. The energy time axis will be 100 samples per second. And we'll be able to see how the energy, this orange curve, basically it matches the amplitude of the speech signal. It's scaled up, right? Because I took the sum instead of the average. If I take the average, it should be actually the same, almost exactly the same size as the speech signal. Maybe a little bit less because it's the average instead of the sum. Oh, average, it looks like it's a lot less. So let me go ahead, go back to the sum. The sum seems to be clearer. Right, so the energy is just the sum over 25 consecutive milliseconds of the amount of energy in that speech signal. And not all of the samples have high amplitude, but plenty of samples have high amplitude. Basically, every time my vocal folds close, there's a high amplitude pressure spike. And that high amplitude pressure spike shows up as energy in energy signal. And when we have silences in between the syllables like this, we can detect where the syllables are by looking for drops in energy. Every time the energy goes back to nearly 0, that's a syllable boundary, right? So we have ah, e, u, a, o, with silent periods in between, zeros basically in between. And so we can detect the beginning and ending of those syllables by basically looking for times when the energy is greater than, say, 10% of the maximum. The maximum is here, and 10% of the maximum is down here, right? So basically, every time the energy rises above 10% of its maximum, we can say that's speech. And every time it's below 10% of its maximum, we can say that's silence. And that's a pretty good way of detecting where the boundaries are of the frames. So I'm going to say that the voice activity detector is an array. And that array contains a 1 if the energy is greater than 10% of the maximum energy. Otherwise, that array contains a 0. So the voice activity detector, the VAD, will just be a 1 whenever the energy is greater than 10% of maximum and a 0 otherwise. And when I plot that, it's this nice binary indicator telling whether there's a vowel there. Maybe, looks like maybe we could have cut it down to a little bit less than 10%. I wonder if 5% would be any better. Let's try 5% and see if that looks better. Yeah, 5% looks a little bit better. So there's the voice activity detector showing the beginning and the ending of every vowel by basically checking to see when is the energy larger than 10% of its maximum. And we can use that in order to separate it into 5 separate words. So we can take the start time. A start time is a time, m times the frame skip, such that the voice activity detector is 0 just before that time. And at that time, the VAD is 1. Right? So the start times are times when VAD of m minus 1 is 0 and VAD of m is 1. The end times are times when VAD of m minus 1 is 1 and VAD of m is 0. Right? So we're looking for these onsets. Those are places where it goes from 0 to 1. And we're looking for offsets where it goes from 1 to 0 again. The start times are the onsets. The end times are the offsets. There should be 5 start times and 5 end times. And then the segments are those speech signals. It's just the speech signal going from that starting time to that ending time. So that the speech signals should be 5 separate signals, one for each vowel. So now it's computing the start times and the end times and generating the 5 signals. Well, I need to do this here. Start frames is not. Oh, I've got a typo here. I called this start frames instead of start times. All right, now I should be able to plot it. And now we can plot segment 0 is the ah, segment 1 is the e, segment 2 is the u, segment 3 is the ah, e, u, a, and then segment 4 is the o. So we can go through those one at a time. Segment 0 should be the ah.
ah,
Segment 1 should be the e.
e,
Segment 2 should be the o. We can just check these one at a time.
u,
Segment 3 should be the a.
a,
And segment 4 should be the o.
o,
All right, good. Now we've got one example of each of the 5 vowels produced in my voice. Now what we're going to do is create a speaker-dependent automatic speech recognizer. We want to create a model that will recognize any one of those 5 vowels if it's said the way that I say it. And the way that we'll do that is we'll create an average spectrogram for each of those 5 segments. We'll create a spectrogram, and then we'll average along the time axis in order to create a Fourier transform that represents the average magnitude Fourier transform of each one of those 5 segments. So an automatic speech recognizer is a piece of software that listens to speech and prints out the corresponding text. And the core is something that we call a model. The model is just a description of what each of the different words or phonemes of that language sound like. So the model needs to be represented in some form that allows easy comparison between different recordings of the same word. For example, a spectrogram. So let's create a frame length, and we'll use a wideband spectrogram here. So we'll just create a frame length which is only 4 milliseconds long. That allows us to get rid of the pitch and to only smooth it out so that all that we see are the formant peaks. Remember, the wideband spectrogram allows us to distinguish between the different vowels, between ah, e, u, a, or o. So we'll use a frame length of 4 milliseconds, a skip of only 2 milliseconds, and then we will calculate the spectrogram of each of those 5. We'll divide each of the 5 segments into frames, right? So X will be segments of K, and then we'll take X from M to M plus capital N, right? And then we'll take its magnitude short time Fourier transform, and we'll take its spectrogram. We'll convert it to decibels. And then if we plot that, we see here's the spectrogram from ah, and you can see that it has peaks at 750 and at 1000 hertz, and then another one up here at 2500. The E has a peak at 250 and then another peak at 2250, and then maybe its third peak is at 2750. The U has a very low peak at 250 and another very low peak at 1250. So the U has its second peak similar to the ah, but its first peak similar to the E. The A has its first peak down here at 500, so it's a little bit higher than E or U, right? And its second peak for the A is up here at 2000, so it's nearly as high as the E. So the A and the O both have their first peak at 500, but the O has its second peak similar to U, the A has its second peak similar to E. Right? So A and O look similar in the low frequencies, E and A look similar in the high frequencies, O and U look similar in the high frequencies, and Ah looks like none of those. Ah is different from all of them. So now we have spectrograms of each of those 5 examples. And now we want to turn those spectrograms into models of what we're looking for when we look at a test utterance. I'm going to say something new, some completely new utterance, and we want to be able to recognize when each of those 5 vowels has been produced. So we have the set of sounds, the Y is the label. The label Y is either A, E, U, A, or O. And the feature vector is going to be one row of a wideband spectrogram. I'm going to take one of these columns, actually, one of these frames, and I want to recognize when a new spectrogram contains something that looks E-like versus something that looks A-like. I want to be able to tell the difference. And the way that I can do that is just take this entire spectrogram of the A and average together its frames. So I'll take the sum over all of the frames, x of m, comma, where m is the time index, and the colon here represents frequencies. And I'm going to create a model, m of y, which is the spectra from the A spectrogram all averaged together, where L of y is the length of that frame. So I'll take the spectrogram of vowel K, right? And that spectrogram is time and then 0 to n over 2, right, is the frequency axis. I'm only going to keep the low frequencies. And I will average it along axis 0. Axis 0 here is the time axis. So I'm averaging it over time. I'm just going to average each of the spectrograms over time in order to show what those 5 vowels look like. And now we can see that frequency in hertz is on the f-axis. We can see that ah has a big peak. It has a peak at 800 and another peak at 1200 that are kind of merged together. And then its third peak is at 2500. E has a peak at 250 and then two more peaks at 2000 and 2500. U has peaks at 250 and at 1000 and at 2500. A has peaks at 500 and at 2000 and 2500. O has peaks at 500 and at 1000 and at 2500. So again, A and O look very similar to each other at low frequencies. At high frequencies, A looks more like E, though not quite as sharp. O looks more like U, right? Looks more like U, except that this 1000 hertz peak is not as dominant in the O as it is in A, because the 500 hertz peak is kind of overshadowing it. So you can see that U and O are similar at high frequencies, A and O are similar at low frequencies, and A is like nothing else. All right, so we can take those, and now we're going to use those as examples. We're going to call that the model. This is a model of an A. That's what an A should look like. It should have a spectrum, a log magnitude short time Fourier transform that looks like this. E, this is a model of E. It should have a spectrum that looks like this. U should have a spectrum that looks like this, and so on. So we're creating a model separately of each of these 5 vowels. And now all we have to do is to use them in order to recognize the speech. So let's load a test utterance, which will be those same 5 vowels, but in a different order.
E, E, U, A, O.
And also much shorter, right? E, U, A, O. So I've got silences in between the vowels to make them easier to recognize, but they're in a different order. And what I want to do is I want to use these 5 models and apply these 5 models somehow to recognize the speech in these 7 syllables. E, U, A, O. Right? 7 syllables in some arbitrary order. I want to recognize which syllable occurred in which order. And the way that I can do that, well, first of all, I divide it up into using a voice activity detector. So I'll calculate the voice activity detector that divides it into 7 consecutive syllables. And then I'll divide those into 7 consecutive segments. Segment 0, 0, 1, 2, 3, 4, 5, 6. Right, so this should be E, U, A, O. And we can kind of see here that segment 0 and segment 2 are similar, but they're not identical. Right? Recognizing that segment 0 and segment 2 are the same is not so obvious. In order to make it more obvious, we want to take the Fourier transform and compare the Fourier transforms to these. Right? We want to take the log magnitude Fourier transform of the first syllable and compare it to these 5 examples and see, is that first syllable an A, an E, an U, or an A, or an O? We'll do kind of a, take every one of these 7 syllables and compare every one of these 7 syllables against all 5 of the vowels that we know. So we've got 7 times 5, we've got 35 comparisons. And then for this syllable, we'll check and see which of those five best matches. For this syllable, we'll check and see which of those five best matches. And so on for each of the 7 test syllables. So we'll calculate the spectrum of each. We'll call those test spectra. And each of those we'll get by taking the test segment. And then we'll take the Fourier, chop that test segment up into frames. Those frames will be 4 milliseconds long. Take the Fourier transforms of those frames, compute a spectrogram from that test segment, and then take the average of that spectrogram in order to find what is the average spectrum of each of the test segments. And we can plot those average test spectra. Here they are. Here's segment 0. Here's what its test spectrum looks like. Now remember this, it has a peak at around 250, and its next peak is really up here at around 2500 and then 3000. If we go back to our models, it definitely isn't an ah. It might be an e. There's that peak at 250 and another one at 2000 and 2500 instead of 2500 and 3000. So that first test spectrum looks kind of like E. It doesn't look anything at all like U. It looks a little bit like A, and it doesn't look anything like O. So that first syllable looks like it might be an E or an A. We have to somehow do a comparison of that first spectrum to these 5 examples and figure out which one it most resembles. Right, so we've got this test spectrum. We want to see which one of those vowels it most resembles. Similarly, this next spectrum, which one of those vowels does it most resemble? And similarly, all the way through for the rest of the spectra. Basically, we're going to subtract each of those 5 vowels from this spectrum and calculate the distance. But the way that we'll do that is something called cosine similarity. Wow, this is a very enlarged version of this picture. I wonder if I can get that figure from its original location. Let me go to the Wikipedia for cosine. No, I can't. Okay. So here's I know. I can reduce the size of the window. That'll probably reduce it. There we go. So the idea of the cosine similarity is to treat each one of these as a vector. Remember, each one of these actually has only n over 2 samples. It looks like a continuous plot, but it's a continuous plot that only has this many samples. Capital N is 4 milliseconds. 4 milliseconds at 8,000 samples per second. Where did I define capital N? Here we go. Capital N is 0.004 times Fs. Fs is 8,000. So 8,000 times 4 1,000ths. Well, that should be just 4 times 8 is 32. That should be just 32 samples. So each of these spectra is a 32-dimensional vector, right? There's 32 numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I don't know. Maybe we can plot them using a stem plot, and that'll show us the spectra, show us the 32 numbers that are included in each of the spectra. Here are the 32 numbers for the ah. Here are the 32 numbers for the e. Is that really 32 or is it 16? Oh, it's n over 2, not n, so it's actually only 16. Each of these is only 16 numbers, right? And so the idea is that we treat those 16 numbers as if it was a vector. Now, vectors, normally we think, if they're drawn on a flat piece of paper like this, a vector is 2 numbers. How far in the x direction and how far in the y direction, right? In 3 dimensions, we might have x, y, and z. Now we're going to have a 32-dimensional vector, right? But you know from geometry that the cosine of the angle between 2 vectors is defined by the dot product between those 2 vectors. So this is what dot product means. If we take the dot product of vectors x and y, that's equal to the magnitude of x, the length of that vector, times the magnitude of y, the length of that vector, times the cosine of the angle between them. So if x and y are 90 degrees apart, then the angle is 0. And the cosine is, the angle is 90 degrees, and the cosine will be 0. X dot y will be 0. If x dot y is positive, that means the angle is less than 90 degrees. If x dot y is negative, that means the angle is greater than 90 degrees. And so we can look at that and we can say, oh, well, this spectrum 1 here, the positive values match pretty well with the positive values for awe. The negative values match pretty well with the negative values for awe. So if we take each of these elements and multiply each of those elements with the awe spectrum, right? We should find that when the awe goes up, test segment 1 goes up. When the awe goes down, test segment 1 goes down. And so we should find that x dot product with y is a large positive number. So we compute the distance between them by taking what's called the cosine similarity. We take the cosine of the angle between them, which is x of k, the test segment, dot product with m of y, the model, divided by the absolute value of x, divided by the absolute value of m. Right? So we get the cosine of the angle between them measures how similar those two vectors are. It's just the dot product of x and m divided by the norm of x divided by the norm of m. So that's defined down here. The dot product is the sum over I of x of I times m of I. The norm of x is the square root of the sum over I of x squared of I. So we can calculate the cosine of each model compared to each test segment, right? So this will be 5 models and 7 test segments. For each of the possible models, we'll take each of the possible test spectra. Here's the test spectrum. Here's the model. We'll take the dot product between x and m and divide that by the square root of the sum of the square of x times the square root of the sum of the square of m. And that should give us the cosine between y, between models of y and test spectra of k. Right, so we can look at the test versus model similarities, and we find that test segments 0, 1, 2, 3, 4, 5, 6, we find that test segment 0 is most similar to E and second most similar to A. Test spectrum 1 is most similar to A, and it's not very similar to any of the others. Test segment 2 is most similar to E and second most similar to A. Test segment 3 is most similar to A and not very similar to any of the others. Test segment 4 is very close between U and O, right? So we have E, A, and then this is either U or O. It's not easy to see from this image whether it's closest to U or O. We'll have to do a careful comparison of those two cosines to see which one is most similar. Test segment 5 is definitely an A, and test segment 6 is definitely an O. So we have E-A, UAO, or EA, OAO. Not quite clear which one is going to turn out to be. We'll have to do a detailed comparison. So we can take the test output. We can take the cosines of :k for k and range length test spectra. So for each of the test spectra, we'll take the corresponding column from this cosine similarity measure, and we'll find its maximum. We'll find out which of the vowels best matches that kth test segment. And then we'll look up its corresponding label. And then I'm going to plot those figures. In each figure, I'll plot the waveform, and above it, I'm going to set the title equal to the test output from the kth waveform. So just running through that, we see that we get E-A, U-A-O. So we find that, in fact, yes, the U was the most similar. Let's actually plot those. Let me find out what the value of, let me add an extra code segment in here, and let's find out what the values for U and O were in test segment 4. Let's print cosines :4, and that should tell us what were the actual cosine distances. So A, E, U, A, O, we see that U was a little bit larger. U was 0.997 and O was 0.995. And so it did correctly recognize the fifth segment as being an U. That's the basic idea of automatic speech recognition. What I really wanted to get across this week was this idea that speech recognition, we take each of the test segments and we compare it to each of the models. So it's kind of an n squared problem, right? You have the number of test segments multiplied by the number of models. For every test segment, you have to check it against every single model in order to see which one is best. And the cosine distance is a good way to do that evaluation. The cosine distance is something that we use over and over again in every neural network and every other recognition system for the rest of the course. All right, let's do the homework. Let me open up the homework assignment. All right, so the first one we have to calculate the voice activity detection, then we have to calculate segments to models, and then we have to recognize speech. So first of all, I want to extract the segments that have energy greater than 10% of the maximum, calculate the energy in frames that have a 25 millisecond frame length and a 10 millisecond skip. So let's first of all do that. We'll say frame length is equal to the integer of 0.025 times fs, and frame skip is the integer of 0.01 times fs. And then we want to take that input waveform and divide it into frames that are 25 milliseconds long with a 10 millisecond skip. For m in the range starting from 0 and going to the length of the waveform minus the frame length, with a skip equal to the frame skip. All right, there are the frames. And then in each of those frames, I want to calculate the energy in each of those frames. So energies. So I want to square the frames and then I want to add them. Let's see, this is going to put each frame in a row of the matrix. And so if I want to add the square within each frame, I have to add it along axis 1, along the columns axis. And then what I want to do is I want to return a segment, which is a list of the waveform segments where the energy is greater than 10% of the maximum. So first of all, let me just do VAD. VAD is equal to a 1 if energies of M is greater than 0.1 times the maximum of the energies. Else 0 for M in the range between, in the range of the length of the energies. All right, that should give me a list of the voice activity detections. Let's turn that into an array just to make things easier. And then what I want to do is I want to find where the frames start. And that'll be the places where M, if M for M in the range of the energies, let's say from 1 to energies, if VAD of M is equal to 1 and VAD of M minus 1 is equal to 0, and the frame ends will be M for M in range of 1 to energies. If VAD of M is equal to 0 and VAD of M minus 1 is equal to 1, and then we want to create a list of segments. And that will be a list of the waveform from frame starts of K to frame ends of K for that waveform, for K in the range from, up to the length of the frame starts. So for each frame start, assuming that the frame end is also available, then we calculate that segment, and I want to return the segments. All right, there we go. That should calculate all of those segments. I've calculated the frame length, then the frame skip, and then I've converted the speech to frames. Then I've calculated the energy in each frame, and the voice activity detection, and the frame starts, and the frame ends, and the segments, and I've returned it. Let's see if that gives us a good enough result to use. Oops, it looks like I've got a typo. Closing parenthesis does not match opening parenthesis in line 19. Here's line 19. In that range, oh, I've got an extra open parenthesis there. That closing parenthesis and that closing parenthesis. All right, that looks like that's right now. Let's try it again. Okay, no typos. Now let's see if we actually get segments that look like this if I run it. I'm going to run homework9.vad and see if it gives me segments that look right. Oh, it didn't. For M and range from 1 to energies. No, I need the range from 1 to the length of the energies, don't I? And here again, I need the range from 1 to the length of the energies. Okay, let's see if that works. That doesn't look right. In fact, each of those frames is only 40 samples long. Let's go back here. We have each waveform segment is frame length long. The energies are the square of the frames and then summed. We want the frames where the energies M is greater than 0.1 times the maximum energy. And then we're summing this along axis 1. That's along the frame. Let's print and say, let's print out what the energies are. All right, it told me that the waveform is 43,000 samples and I have 537 frames. And I have a frame length of 200 and a frame skip of 80. Those sound correct. If I've got 10 millisecond skip and 25 millisecond frames, then it should take 43,000 and divide it into 80 sample frames. Should give me 43,000 divided by about 100 is about 537. That seems reasonable. The waveform then is going from frame starts of k to frame ends of k. Let's print out what frame starts and frame ends are. Actually, let's print the VAD and just make sure that the VAD has 537 with a reasonable range of ones and zeros in it. Okay, there's the VAD, and it looks like it has 1, 2, 3, 4, 5 segments. Good. 5 segments with +1 VAD. All right, that looks reasonable. Let's find out what the frame starts and frame ends are. Oh, I see what the problem is. Look at this. I'm starting at frame start instead of the time start. I need to multiply that times the frame skip parameter. There we go. Because that's how many samples there are per frame. I don't want to just go from the beginning of the frame. I want to go from the time of the beginning of the frame. All right, let's try that. All right, those look like the waveforms I want. I've got a, e, u, a, o. Now I want to convert each of those to a model. Let's see, segments to models. I'm given a set of segments and a sampling rate, and I want to return a list of models, which is a list of the average log spectra. All right, so from each of those segments, I want to create a spectrogram. So I will create models this will be a list. And then for k in the number of segments, what I want to do is I want to take x is equal to, well, let's call it waveform actually. Waveform is equal to segments of k. And then from there, I just want to calculate the spectrogram of that waveform, but with a 4 millisecond frame length, not a 2 millisecond, not a 25 millisecond frame length. So the frame length and the frame skip now are going to be 4 milliseconds and 2 milliseconds rather than 25 milliseconds and 10. All right. Now I want to take the waveform and chop it up into frames, and then I want to take the Fourier transform, the absolute value of the Fourier transform of each of those frames. Along axis 1. And then I want to calculate the spectrogram, which will be the, oh no, just the spectrogram first. The spectrogram is going to be 20 times the log base 10 of the MSTFT. And let's see, I want to divide that by the maximum. And then I want to take the maximum of 0.001 for that spectrogram. So if it's greater than 1/1000th, then I'll just take its logarithm. Otherwise, I'll clip it at 1/1000th. And then finally, that should give me the spectrogram. So then I just want to calculate the model. I want to append to the model the average of the spectrogram along the, oh, and I want just 0 up to the integer of the frame length over 2. And I want to take the average along the time axis. And then I want to return those models. Let's try that and see if that solves all the problems. So I've got the frame length is 4 milliseconds, the frame skip is 2 milliseconds, and then I've calculated the waveform, chopped it into frames, calculated the magnitude short time Fourier transform, calculated the spectrogram, and then appended that to the model. Let's see, first of all, if there are any typos by just running the code. Looks like there are no typos. All right, let's see if I can create a reasonable model of each segment. There's the A, E, U, A, O. It looks like I probably want to pre-emphasize those, doesn't it? Let's see, up here, did I pre-emphasize these? Oh yeah, look at that, I pre-emphasized those. I took the subtraction between x and x of n minus 1. So let's take the x is equal to waveform. Let's call this x. And then we'll take x of m plus 1 to m plus frame length minus x of m to m plus frame length minus 1. That should pre-emphasize it. Let's see if that looks more reasonable. Waveform is not defined. Oh, because now I've called it x. X is equal to segments of k, frames is equal to the difference between x of m plus 1 to m plus frame length and x of m to m plus frame length minus 1, up to the range of length x. There we go. All right, those look like the models we want. There's A, E, U, A, and O. And now we want to take a test waveform. We'll take in a test speech signal and the set of models and the set of labels. And what we want to return is the cosine similarity of each model to each test segment, a y by k array, and the test outputs, the actual recognized labels. So again, the first thing we're going to do is to calculate a spectrogram, and this will use a 4 millisecond and 2 millisecond. Well, let's see, spectrogram is down here. Let's see, I want n is equal to the integer of 0.004 times fs, and s is equal to the integer of 0.002 times fs. And I want to calculate the frames is equal to test speech of m to m plus 1 to m plus n minus the test speech from m to m plus n minus 1 for m in the range from 0 to the length of the test speech minus s minus n with a skip of s. There's the frames. Now I want to calculate the magnitude short time Fourier transform. And then I want to calculate the spectrogram. Oh, so first I want to chop it into segments using VAD. All right, so first I want to chop it into segments. Segments equals VAD of the test speech. Okay. And then once I've done that, then for each of the segments, I want to calculate its spectrogram. And the spectrogram will be 20 times the log base 10 of the MSTFT, the maximum of 0.001, or the MSTFT divided by the array maximum of the MSTFT. All right. And then I want to take that spectrogram and compute its average. Before, the models were the averages, right? Yeah, I took the average here along the time axis. So I want to calculate the average of the spectrogram from zero to the integer of n divided by 2. And I want to calculate that average along the time axis. And then I want to calculate the cosine distance between that spectrum and each of the models. So first, let me create a Sims matrix. This should be a y by k array. So the first axis should be the length of the models, and the second axis should be the length of the segments. And now I want to calculate for each of the models, for y in the range of the length of the models, I want sims of y comma k to be the dot product between the spectrum and the model divided by the vector norm of the spectrum times the vector norm of the model. This will be linear algebra norm, I think. I think NumPy linear algebra norm computes the length of the vector. If I remember correctly, let's find out. All right. And once I've done that for every possible model, then I want to create a test output. The test output here is a list of strings. So I want to append to the test outputs the label corresponding to the argmax of sims of the kth test segment. So I've got the set of cosine similarities for the kth test segment. I want to take the argmax over that array and then use that in order to look up the label. Then I want to return the sims and the test set outputs. Let's see if that works. First of all, let's check to make sure we don't have any typos. Oh, there's a closing parenthesis that doesn't match after test outputs append. Let's see. Test outputs append labels of NP argmax. There we go. Check for typos. Looks like there's no typos, so let's check for the similarities. We should recognize e a o. Let's see if it recognizes that. It recognizes e-a, u, a, o. Looks like we've got it. Let's check the automatic grading code to see if it works. It looks like 100%. All right, in that case, we can open up GitHub Desktop and check it in and finish the assignment. Let's commit those files to main, push it to the origin. There we go. And then let's go to github.com and check to make sure that it got checked in correctly. Let me switch from my teacher account to my student account. And in my student account, let's make sure that homework 9 got checked in correctly. And there's all the code for VAD. There's all the code for segments to models. There's all the code for recognized speech. So we can take this URL and copy it and go back to this week's assignment, homework 9. And we can go ahead and paste this in. Please enter the URL of your copy of homework 9. All right, that's all for this week. So let me go ahead and stop the recording.